This lesson deals with supplemental problem 13.3. You can find this problem in the ECE202 ebook in the Chapter 13 supplemental problem starting on page 6. I'd like you to run the following PSpice file, plot all the node voltages, and also print the Fourier components. Let me explain the circuit and the file that goes with it. So I have a title. My input is a sine wave with an amplitude of 4 volts and a frequency of 60 hertz. So the command to be sine, average value, which is 0, peak value 4, frequency of 60 hertz. I need a resistive path back to ground for the voltage source. I'll put a resistor there of 1K, although the value doesn't really make any difference. Then the voltage that's here, I'm going to use a voltage-controlled voltage source to create a voltage here that's a math function. So the output terminals, plus and minus, are between 2 and 0. And now we're going to use a different command in PSpice and say value is equal to squiggly brackets, and then ABS stands for absolute value, of the node voltage V1. Close the bracket, and then close the squiggly bracket. So whatever voltage is present here, what's going to show up here is the absolute value of it. So when this is positive, this will be the same positive value. When this is negative, this will be the negative of that value, which is then be positive. I have an RC filter, a 1K and a 5 microfarad capacitor. And then I'm going to ask for the Fourier series with my fundamental frequency being 60 hertz and my node voltage V3, the output. I'm going to print 5 cycles. So 5 times 1 over 60 is 83.3 milliseconds. I'm going to divide that by 2,000 so I get a lot more data points on the screen. I'm doing some comparison with hand calculations. Start printing my results at time 0 and then make the sealing step the same as the print step. I'd like you to use the textbook to find figure 13.4, which is the figure that shows the Fourier series of a lot of different waveforms. This may change with future versions of the textbook, and find the one that's called full wave rectification. We'll use the Fourier series that's there instead of driving it ourselves. Find the average value of V out, which is actually node voltage 3. And let's find the forced response of V out, and we'll compare the results with PSpice. So running my simulation and plotting in this first plot, V1, which is our input voltage, which is a 4-volt sine wave at 60 hertz. So you see I have 5 cycles. The output of our controlled source is the absolute value of this. When the input's positive, I have the same value. When the input's negative, I take the negative of that. Basically slices the waveform and folds it over. In ECE202, we'll take a look at a circuit that does this, or pretty close to this, called a bridge rectifier. So I had a frequency here of 60 hertz. I've now created a frequency that's double, so 120 hertz, plus also other harmonics. The next graph is that of the output of the filter. You can see here in steady state, I eventually approach a sine wave. Also, we requested the Fourier analysis of node voltage 3. You can see here that when you look at the odd values of n, that the Fourier magnitude term is very small. And we could say, since it's several orders of magnitude away from the even ordered harmonics, we say that the odd harmonics are equal to 0. In fact, when we look in our textbook in figure 13.4, we'll see exactly that. And here's the corresponding phase angles. Now that we have the simulation done, let's turn to our next task, which is going to do some calculation and comparisons. So if you go to the textbook and find the figure that has quite a few waveforms on it and the Fourier series for those waveforms, this is figure 13.4 at the time of this recording. This is the Fourier series that's listed in that table, evaluated at our frequency of 60 hertz. So it's in terms of the amplitude A, but it's also the even components only. We saw that in the table from the simulation. Evaluating this equation, when A is equal to 4, I get 2.546, and this term is double that. And then I have 1 over 1 minus n squared, and then the cosine of 2 pi n 60t. The value here is the average value of our waveform. In our circuit, a capacitor is an open circuit for DC, so we'll have no current flowing, and so the output voltage will be the same as the input voltage for low frequencies or DC. So our average value at the output will be 2.54. That's exactly the value here. And we saw on the previous page that the value for A0 was 2.546451. What's effectively happened is that we took a waveform that has an average value of 0 and turned it into an average value of 2.546. For the other components that are there, we have 60 hertz components and we have multiples of that, although some are very small. This filter will allow some of those components through, but with attenuation as the frequency increases. Let's analyze this circuit and see what it does to the various components in the Fourier series. So the value of our frequency is S is equal to j omega, and what we have is something that's a multiple of 60 hertz. This will be equal to 377 times n and then j. So I have a voltage divider here with the capacitor's impedance and the resistor. And the impedance of the capacitor is 1 over SC, and that's 200,000 over S. So that's my numerator over that same value plus 1K times V n of S. Multiply numerator and denominator by S. So you just get S times 1K, and then divide by 1K, and you get 200 and 200. So 200 over S plus 200 times Vn. Plugging in S equals j omega from here, I have 200 then plus j 377n. My input voltage is, if you scroll up to the top, is the amplitude that's multiplying our cosine function, and that was 5.093 divided by 1 minus n squared. Then we have our cosine function, which has an angle of 0. Let me pull the minus sign out. So I have n squared minus 1, and then put that minus sign over here as a phase angle of 180. So then my magnitude is 5.09, n squared minus 1, which will always be positive, and then the magnitude of the denominator, which is the square root of 1 squared plus 1.885 n quantity squared, which would be 3.55 n squared. And then my angle is going to be 180, and then minus the angle of the denominator, which is going to be the arctangent of 1.885 n divided by 1. So I evaluated this at the bottom of the page. Different values of n, and this is my value calculated from above, my magnitude and angle for the different values of n. Now if you go back to the previous page, we can also pull off the values of the Fourier components. You can see that the magnitudes are very close to each other. My phase angle, though, is in terms of a sine wave, so I need to shift that. Take my angle from the simulation, subtract 90 degrees, and then add 360 to it so I can get it back looking like this term. At 103.4, 94.7, 90.7, and 88. So again, very close to the angles that I had found on my hand calculation. What's happening is that we're able to take a waveform with an average value of 0, taking its absolute value, or we call full wave rectification, and passing it through a filter. We pass the DC component, which is our average value, which is what we're actually trying to do with this. We're trying to turn it into a DC power supply, and then filter out the components that are present, or make them smaller. And this is supplemental problem 13.3.